Yes, today we're going to start chapter 3. Before we can start chapter 3, though, we're going to go back and address something from chapter 1 that we had skipped. And that was intentional. Like with the traditional class, we always handle this chapter 1 topic later. We don't do it in the very beginning for whatever reason, but that's the way we just set the course up. So we're going to look at section 1.8 right now. Which is about transformations of functions. And I'm going to do this kind of in the barest bones fashion, so I'm just going to kind of concentrate on like what we need to know and how we need to use it for this class rather than doing this like deeply and theoretically. We okay with that plan? Okay, so this is the big idea. So we can take any function, we'll call that function the parent function, and we can transform it into some new type of function by multiplying or adding or subtracting in that following fashion. So this is, that's a C there. That's a C. It's just the name of the letter. For whatever reason, this course we're calling it C versus B that you might have called it before in a previous course. It's the same thing. I'm not going to be, what?
Horizontal stretch.
Yep. But we're still talking about the same thing. So when we talk about transformations, maybe even this is too far ahead. Let's take one step back and just kind of remember what we meant by a transformation. So in your geometry class, oh my gosh, what is going on? This thing is enormous. You would have talked about transformations. And in that class, you would have talked about 4 types of transformations. Why is that so big? Whatever. So those 4 types of transformations were called translations. So that's a situation where you're moving things from left and right or up and down. So let's say we have, this is our parent function. So a transformation of that would be, our translation of that would be something like this, where I've moved it left or right, or up or down some amount, but the orientation of the thing is still the same. Notice the triangle is still pointing up. And the size of it's still the same, like it's still the same size as it was before. It basically just picked it up and moved it to a new location, but other than that, everything else has stayed intact. Everybody's okay with that idea? Okay. We also talked about reflections there. And specifically, the 2 types of reflections that we're worried about are when we reflect across the x-axis and if we reflect across the y-axis. You can really reflect across any straight line, but that's beyond the scope of this class and really almost any of your high school classes. Here we're just going to worry about if we reflect across the x-axis or y-axis. So if I reflect across the y-axis, I'd get something like this. Notice that this distance is about the same, or should be the same. It looks about the same. The shape of the figure is still the same. The orientation remained the same. Everybody's okay with that? If I had reflected across the y-axis, though, you'd notice there that the orientation does change. That's not quite exactly right across, but it's close enough that best I can do with no grid to really line things up nicely. But the distance from our original to the x-axis and our new one, our reflection to the x-axis, is still the same, but the orientation has changed because basically we've just folded across. But the shape is still the same, the size is still the same. Leo?
Can a translation also be a reflection?
You can do both at the same time, but and for example, that reflection across the y-axis you could describe as a translation, right? So sometimes, I guess I would say. The third type of thing we talked about there were dilations. So with a dilation, probably look like right about there. Things are going to get bigger or smaller, and then they'll, depending on how you're doing the dilation, likely the location is going to change a little bit also. And then the fourth thing that we talked about in your geometry class were rotations. That's beyond the scope of any algebraic class you take as a high school. We're never going to talk about a transformation to a function that's a rotational. Jack?
The translation and the dilation work together. Can be purpose.
Yeah, you can do all of these in combination with one another. Yes, absolutely. So we have this algebraic representation of how we can transform some function. And we've talked about what the different types of transformations are. So let's take a moment here and talk about how or what these A, C, H, and K do, right? Like what transformation is happening if I give the C a value or the H a value or whatever. Sound good? So I'm just going to do that verbally. So let's say if C is positive, let's start negative, then we have a reflection across the y-axis. And then if C is positive, we have no reflection across the y-axis. The C controls one reflection. Yes?
Can I move over there and turn my tablet?
Sure. The C also controls a dilation. So if the magnitude of C is bigger than 1, we have a horizontal stretch by a factor of C. So horizontal, again, is left and right. Everybody's cool with that? Again, most of us, I'm sure, knew that, but sometimes it just helps to just confirm it. Like, oh, which way was horizontal? If the magnitude of C is less than 1, we're going to have a horizontal shrink by a factor of C. And if the magnitude equals exactly 1, you have no horizontal stretch or shrink. Notice here again that C can't be 0. Why can't C be 0? Yeah, because you have 1 over c, you can't divide by 0, right? So it doesn't even make sense to talk about c being 0. I'll just write that down, though, in case you're curious. So the c controls 2 things, right? It controls the horizontal dilation, the stretching or shrinking horizontally, and then a reflection across the y-axis. The A also does 2 things. So if the A is negative, we reflect across the x-axis. And if it's positive, there's no reflection across the x-axis. And A cannot be 0, because if it was, your function would just be a constant function, and you've destroyed whatever the original thing you would have been transforming, because you have A times the f of x. So if you had 0 times f of x, it's just 0, and your function just went bye-bye. And that's not interesting. And then same kind of thing with the magnitudes of A. If it's bigger than 1, we have a vertical stretch by a factor of A. And if it's less than 1, it's a vertical shrink by a factor of A. And if it's A is equal to 1, then there's no vertical stretch or shrink. The H and K's control the translations. So if H is positive, we're going to go right H units. And if H is negative, we're going to go left H units. And if K is positive, we're going to go up K units. And if K is negative, we're going to go down K units. You should recognize most of this from last year in your Algebra 2 course, right? When we talked about parent functions with regard to these different function groups. So we always had like this A, H, and K. The C is maybe new for some of us, but so again, this is all stuff that you'd want to make sure you know that criteria. So we have that algebraic representation of a transformation, and we can use that to come up with a verbal description of the transformation. Let's do a couple of examples where we do that. Sound good? So let's say our parent function is just f of x. And let's say our transformation is three times f of negative 2x plus 8 minus 1. So if I want to describe this transformation in words, the first thing I'd want to do is to identify the values for A, C, H, and K. So to do that, I'm going to basically just look at my general transformation. And I should be able to read the values from that. Now there is one little hiccup. If I look inside of my f of x, I notice the stuff inside of my f of x is not in the same form, right? So the biggest thing here is I need to make sure that I am going to factor the inside of that f of x. so that the leading coefficient is 1, like it is in the general transformation that I've written in red. So I'm basically just going to factor a -2 out front. Rami?
How would you just put it as 1 over -0.5?
We'll get there in a second, but you could do that. Does everybody see what I did factoring there? Now that's important because you will not get the correct H value if you do not do that. Okay, you will always mess that up. So critically important that you're remembering to check to see if you can factor inside of the function before you get rook and roll in here. Okay, so I can see that the A value has to be 3. Everybody okay with that? I can see that 1 over C is -2. So if 1 over C is equal to -2, I can multiply both sides by C and then divide both sides by -2. And C has to be -1/2. Everybody okay with that? The easier way to think about it, though, is that -2 has to be the reciprocal of C, right? So I'll just take the reciprocal of -2, and that's my C, -1/2. You don't have to go through the algebra, but I wanted to show you the algebra, so it's like, why is it just the reciprocal? You know, I'm just beating you to the punch there. Okay. I see the H is 4. Remember that the sign in front of the H matters. Since they're both negative signs, I know the H is really a +4. If the signs are different, I would know the sign of H would have to be negative. Everybody's okay with that? And then the K is -1. Notice because the signs in front of the K's are different, I know that the K has to be negative. Everybody okay from there? So this is typically the trickiest part, is just making sure you're able to correctly identify those values. From here, I'm just going to be using the criteria above. So since the C was negative, I know that I have a reflection across the y-axis. And since the absolute value of C is less than 1, I know I have a horizontal shrink by a factor of 1/2. Since my A value is positive, I don't have any reflection across the x-axis. On your assignment, if nothing is going on like that, you don't have to write that nothing happens. But I'm going to do it in the notes just so I'm being consistent. Because the absolute value of A is greater than 1, I have a vertical stretch by a factor of 3. Since the H is positive, it's going to go right 4 units. And since the K is negative, it's going to go down 1 unit. Jack?
We have to do this on a test. We have to have that whole thing memorized.
Yeah.
Right.
The good news is it was basically the same criteria you used last year, because we did do this last year in your Algebra 2 course. And it's always the same. So it's just like, you know, it's always the same. But yes, you should know that criteria. So when you're doing the homework, also try to like work on doing the memorizing of it at the same time. You know what I mean? Like, don't wait and just try to memorize it separately. Like while you're doing the homework, it's like, okay, got my values. Let's try this once on my own. No, okay, so let's go back and revise. You know, okay, I'm gonna try it again on my own and just, you know, work on it at the same time. That's what I would do anyways. Okay, so this one was real general, this example, because our parent function was just like an f of x, right? What if we have something that's a little more specific? What if the parent function was, say, x cubed? And our transform function maybe was actually, let's do that. So my general transformation, we said, was this, right? That's what we said at the beginning. But here, well, let's maybe make it a little easier to see. Let's, instead of calling that y, we'll call it f of x. Here, my f is x cubed. So what I'm going to do is I'm going to take this f and I'm going to replace it with cubed. So f is what the function is doing. In this case, that function is just cubing something. So whatever was inside of f just gets a cubed on the outside of it. Is everybody okay there? So again, got to make sure I check the insides. I notice the leading coefficient on my x is not 1, so I'm going to have to factor that out. So I factor out the 2x, and then what's the next thing going to be?
Plus 3.
Well, when I factor something out, what operation am I doing?
Division.
Division. So I'm going to have 3 divided by 2.
Oh.
Now you could write that as a decimal, but I'm just going to write it as the fraction 3 over 2. Is everybody okay there? Okay. So my a is -2.
Does our square go away?
Well, I just chose not to write. I mean,
Okay.
because I'm just,
Yeah, no, go ahead.
yeah, this piece is that piece, so it's just,
Yeah, no, I know what you're talking about.
that's okay. Those underlines, because I'm using the green here. My 1 over c is 2. So what's my c then?
Opposite.
It's the reciprocal, so 1/2, just reciprocal. The sign doesn't change, just reciprocal. My h is going to be -3 over 2. Notice the signs in front of the h's are opposite, so the h has to be negative. And then my k is -5. Notice the signs in front of the k's are opposite. Everybody okay there?
You go over how you got.
Sure. So let's look at a simpler example real quick. So if I have like 2x plus 6, if I factor that 2 out, I get 2x plus 3, right? Because the 2x turns into the x by dividing by 2, and the 6 turns into the 3 because I divided by 2. So the same thing's going to be happening here. I take the 2x and I divide by 2 to get the x. and I take 3 and divide it by 2, that's the same thing as 3 over 2. Is that okay? You could write it as 1.5 also. That's not wrong. I like fractions because I don't have to worry about, do I round this or not? The answer is don't round. If you have to round, use the fraction instead. It's okay if you use a decimal if it terminates like 1.5. But if that was like, 2 over 3, there I would mark you down if you wrote 0.6 or something. Because it's not 0.6. You know what I mean? So I just use fractions so I don't have to worry about like, ooh, is it okay to write the decimal or not? Ooh. Does that feel okay, Jack? Okay. Okay. Now that we have this, we can just describe what's going on. So the first thing I'm going to check is the C. I notice that C is positive, so what does that mean?
No y. X.
Good. No reflection across which axis, though? X or Y? It's the Y.
Let's do y first and maybe think over twice.
So here's the way I remember these. The C is affecting the X coordinate. If you reflect across the Y-axis, the X coordinate is changing, like it's going from over here to over there. And the other thing the C does, since the absolute value of C is less than 1, it's going to stretch or shrink horizontally. Which one? Shrink. And horizontal, again, is changing the X, exactly. Then we do the A. So the A is negative. What does that mean? So that's the reflection. Good. Which axis?
X.
Okay. And then since the magnitude of A is bigger than 1, it also does a vertical stretch or shrink. Stretch by a factor of 2 in this case. And again, hopefully it's easy to remember stretch versus shrink, right? Like stretch is getting bigger, so it's the greater than. Shrink is getting smaller, so that would go with the less thans. Is that okay? Again, the A is attached to the Y coordinate. So like if you flip it over the x-axis, the y-coordinate's changing. Or if you stretch it up and down, the y-coordinate would change. Okay. The h is less than 0. What does that mean? Means we're going to go left 3 over 2 units. And the k is negative. What's that going to mean? Down 5 units. We okay here? So again, this is just like pretty easy. It's just a matter of remembering the rules and kind of grinding that out. Leo?
What did you do with the cube, though? Or are you going to get to that?
No, it doesn't matter.
So why did you have to plug the cube in?
Well, so if I looked at my transform function here, I wrote it with a square instead of a cubed. There's no f in it, right? It has this x cubed, or has the cubed in it. So I just adapted my general one to match the parent function, which has the cubed in it. You know what I mean? That's all.
So it's not like you have the cube in front.
I don't have to do anything with the cube. I just have to I just wanted to address why the heck's there a cube in this? What do I do with that? The answer is nothing. You just treat it like the general transformation where the cubed is your f of x. Does that feel okay?
Yeah.
Okay.
So we're not dealing with this with triangle, right? It's just like
Right. So f of x is just a general function, right? It could be a graph who looks like a triangle, but it could be like a parabola, or like something else, or like blah, 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 whatever. Doesn't matter per se, but that's why I use the f of x, is just to be really general. But yes, we're talking about how a graph is changing from a parent function, a starting, and then we do some transformation to it, and then we get this new version. Okay? So algebraically, we have everything that we need to like take an equation of a parent function, and if I want to do something to it, like reflect it or stretch it or translate it or whatever, I have the tools now to do that. What if I want to take a graph of a parent function and then change that? So let's look at an example where we have to do that. So the key here, so if I'm taking a parent function, if I take some point on the parent function and I want to transform it, I'm going to take the x-coordinate, multiply it by c and add h, and then I'm going to take its y-coordinate, multiply it by a and add k. So this is my key tool for graphing. So let's say that we have what the heck happened? Okay. So let's say I have a graph that kind of looks like this. So let's say that's my f of x. I'll write it here. And let's say that the points on this function are, say, like, I don't know, -4, 2. We'll say that's -2, -3. That one would be 0, 2. Let's say that's 3, 2. Let's say that's 4, 6. Okay, so this is our example. That's our parent function. And let's say we want to graph -3 times f of x minus, or -x plus 2 minus 1. So the first thing that I'm going to want to do is I'm going to want to pull the values for a, c, h, and k.
We always have to factor out the negative.
So yes, we'd want to make sure that you recognize that we got to factor out that negative. So that part inside turns into that.
But if it's a positive, you can just leave it like that, right?
If it was a positive one, you wouldn't have to do anything.
Oh.
Yes, very good. Okay, so my A is what?
Negative
3.
three.
My C is,
Negative, or 1 over negative 1.
which is the same thing as
Negative.
just -1, right? Yes, it's the reciprocal of -1, but that's still just -1. My H is,
Negative 2.
careful.
No, positive 2.
Yes, it's +2, right? We're looking at
Yeah.
that 2. And then my K is
Negative 1.
-1. Everybody cool with what I did there? So now I'm going to take my transformation map that I gave you guys just a moment ago and fill in the values for my specific transformation. So I have -1 times x plus 2 and -3 times y minus 1. Is everybody okay there?
All those points from the graph.
I plugged those in for my specific A, C, H, and K. Right? C was -1, so in place of C, I put the -1.
So we're just plugging in this.
So I'm just plugging stuff in. H was 2, so where H was, I put 2.
So the hardest part is getting our values for A, C, H, and K.
Yes. And then all I need to do from there is I'm going to use my points on my graph. So I'm just going to copy down those 5 points from my graph. And now they're going to plug into the x and y's in that formula I just wrote. So I plug -4 in for x, and I plug 2 in for y. -1 times 4 plus 2 is 6. And -3 times 2 minus 1 is -7. And I just kind of continue doing that for every point from my parent function. So that's going to give me 4, and that's going to give me -10. Be 2 and -7. So that's going to give me -1 and -7. And that's going to give me -2 and -19. Everybody okay with what I did there? Nothing tricky, right? I just plugged the x's and y's into this little formula that we made to get our new points. And then just I plot my new points and I draw my new graph. So let's see, I have 6, -7. Oh, let's use a different color than red, huh? And then I have 4, -10. This is going to get terribly messy. 2, -7. And then -1, -7. And then -2, -19. So that's my new graph. Ben?
Can I go to that?
Sure. What did you guys think on that?
It's not difficult.
Not that bad, right? You basically, again, the trick just comes down to pulling those values for A, C, H, and K, plugging them into the formula, and then grinding the points through that formula that you just made. But not so bad.
Is that the only, is there more to this, or is it just that?
There's one more type of thing that I want to talk about.
Okay.
And that is, so we've seen how to take an equation of a transformation and decide what it did, right? That's what we started by doing. And we saw how to take a parent function's graph and transform it from an equation. What if I have the parent function and I know what I want to do to it, and I want to find the equation for that? That's the last example kind of thing that we're going to do. So here we're going to say, let's say our parent function is, say, 2x squared minus 3x. And let's say that I want to reflect it across the y-axis, and I want to go right 2 units, and then I want to vertically stretch. Actually, let's do, then we'll go up 5, and then we'll do like a vertical stretch by 3. Okay, so I have this parent function, and I want to do these transformations to it, and I want the equation of the function after I do these transformations. So the first thing I'm going to do is I'm going to determine for each one of these transformations what coefficient is changing and what that value should be. So I'm going to look at the transformation and decide, okay, does that represent A, C, H, and K? And then what the value for A, C, H, and K should be. Everybody good with that plan? So if I reflect across the y-axis, which of the coefficients is responsible for that? A, C, H, or K? C. Okay. And what do I know about C if there's a reflection across the y-axis? It has to be negative. Very good. And because there's no further horizontal stretch or shrink, I know the sign for that C, or that C should be -1. Everybody's cool with that? That'll get you no stretch or shrink, but still will get you the reflection. If I want to go right 2 units, what coefficient is doing left and right?
H.
H. And the value for H should be then?
-2.
+2 is to the right. -2 is to the left.
I was thinking in the equation it'll say +2.
Gotcha. Gotcha. Okay, how about up and downs?
Okay.
Okay, and the value for K should be? 5. Good. And a vertical stretch is controlled by A, and the value of A should be +3, right? Because we have no reflection across the x-axis going on also, so it needs to be +3. Everybody's okay with that? So I'm going to do this transformation in 4 steps. So I'm going to call these intermediate steps, I'm going to put a subscript on it, so like G1 or whatever. And, well, actually, before I do this, let's just restate that this is what I'm using each time. So in this case where C is 1, nothing else is going on. So A is 1, H is 0, K is 0. In this case, H is 1, C is 1, and K is 0. A is 1, C is 1, and H is 0. C is 1, H is 0, K is 0. Why is A 1 when nothing happens? Well, because A is being multiplied, right? What number do you need to multiply by if nothing happens? 1. Why is C 1? Well, C is being multiplied, right? What do you need to multiply by for nothing to happen? 1. H and K are 0, though, because they're being added and subtracted. What do you need to add or subtract by for nothing to happen? 0. Does that all make sense? Okay. So I'm going to do this in 4 separate steps. I'm going to do one transformation at a time. So I'm plugging in my values for A, C, H, and K. So this is really just f of negative x. Everybody okay there? So f of negative x tells me that in my function f, everywhere where there's an x, I'm going to replace that with a negative x. So I'm going to have 2 parenthesis negative x squared minus 3 parenthesis negative x. Is everybody okay with what I did there? So let's simplify things. The order of operations says the first thing I need to do is the exponent. Negative x squared is the same thing as negative x times negative x. Negative times negative is positive. X times x is x squared. So that's going to give me x squared. And then 2 times x squared is just 2x squared. Negative 3 times negative x is going to be positive 3x. And now I'm ready to move to my next step. So in my next step, my h is 2, but I'm going to do that on the previous answer. So that all simplifies down to just g1 of x minus 2. So this guy is inside, so that means everywhere there's an x, I'm going to plug in an x minus 2. Everybody okay there? First thing I need to do in order of operations is the exponents. X minus 2 squared is x minus 2 times x minus 2. To multiply two things in a parenthesis like that, I'm going to FOIL. So I'm going to choose to do this stuff first. So that gives me x squared minus 4x plus 4. And then here I'll just distribute things through. And now I'll distribute my 2 through. So negative 8x and 3x is negative 5x. And then 8 to negative 6 is positive 2. Next step in my transformation, going up 5. So again, I'm doing this to my previous step. So the k is 5, everything else is kind of a null value. So this just turns to g of x plus 5. Oh, well that's really easy. So my my g2 of x is 2x squared minus 5x plus 2. And then I just have the plus 5 at the end. So I just add that together. 2x squared minus 5x plus 7. That one was really easy to do. And then my last one, my G4, the a is 3, and then everything else was like a null value. So that just turns into 3 times G3 of x. Oh, and that's really easy, right? So G3 of x is just 2x squared minus 5x plus 7. So I just have 3 times that. All I got to do is distribute through. That's all I have. That's it. Now there was a lot of simplifying, right? But here's what I would tell you guys, is on like a test or whatever, if I can see like those setups, and if you goof up some of the algebra in between, you know, you'll get 2/3 to 3/4 of the points if you can just get the thing set up and you goof up some simplification in the middles. You know, I would give you the majority of the points there for a problem like that, even if you're like, woof, I goofed up all the simplification. But you could do that setup without even having to do any of the simplification in between. And it would just take like, you know, a minute or two to write that part down. Okay? And I get that some of these can be pretty tedious. In particular, the H's can be pretty tedious. The rest of them aren't so bad. This is where we're going to stop.